Hello and welcome. In this video, we're going to review what we already learned about taking the derivative of functions that involve natural log, so natural log of some function. We are going to build on that and talk about how do we find the derivative of a common log, an log log. How do we convert that into a common log so then we can use the properties of logs and what we know about the derivative of natural log of x to find the derivative. And then we're going to wrap up with how do we use logarithmic differentiation and what is logarithmic differentiation. So let's go ahead and jump in with a little bit of review. So in the limits unit, we actually proved that the derivative of natural log of x is 1 over x, and we did that using logarithmic differentiation. What we're going to do in this video is we're just going to review that a little bit, and we're going to talk about some shortcuts that can help us along the way. So when I look at number 1 here, I see that I have a chain rule situation because I have the natural log of some function. And within that chain rule, I also have a quotient rule. And that sounds like kind of a lot, having to take the derivative of the quotient or of the chain rule and the quotient rule together. It just sounds like a lot of work. So what I want to remind you, my big tip for you in this section, anytime you have logs, don't forget about your properties of logs because they're going to come in handy and they're going to make your life a lot easier. Properties of log. And what I mean by that is expanding is your friend. Expanding is going to turn something that's a chain rule and a quotient rule into something much more straightforward. So if we look at this, and I'm still going to write y equals, I'm not going to actually take any derivatives yet, and I'm just going to expand. So the numerator is going to expand to natural log of 4 plus 2 times natural log of x because the squared sign can drop down in front. And the natural log of 4 and the natural log of x squared can be split using addition because of properties of logs. Minus natural log of the quantity x minus 1. We're subtracting because that's in the denominator. So all of those properties of logs have turned the derivative work here pretty straightforward. Natural log of 4 is just some number. The derivative of some number is 0. The derivative of 2 times natural log of x is 2 times 1 over x, or 2 over x. The derivative of ln of x minus 1 is the derivative of x minus 1, which is just 1, over x minus 1. So minus 1 over x minus 1. This is much easier than trying to work with the quotient within the chain rule. Okay, number 2, even with properties of logs, I can't expand or change this, so I am going to just have to use number 2 is a chain rule problem. So if I take the derivative of the outside function, I get 1 over the inside function, or 1 over u, and I need to multiply that by the derivative of the inside function, and the derivative of cosine is negative sine. So you could rewrite this as negative sine over cosine, or you could rewrite this as negative tangent of x. Dealer's choice. Number 3, this is going to involve using the product rule. So I'm going to take the derivative of x, which is 1, times natural log of x, plus x times the derivative of natural log of x, which is 1 over x. So y prime is natural log of x plus 1. So this was using the product rule. All right. On number 4, I'm going to expand first. So y equals natural log of 3 plus x natural log of x. We actually just took the derivative of x natural log of x, so I'm going to steal this answer. The derivative of natural log of 3 is 0. The derivative of x natural log of x we can take from number 3 is going to be natural log of x plus 1. So keep those properties of logs in mind because oftentimes expanding is going to make your life easier when we're taking these derivatives. And we're going to use a little bit of those properties in the rest of this section. So we talked about the change of base formula in the video that reviewed properties of inverses. And we talked about how if I have log base b of x, that is the same thing as saying natural log of x over natural log of b. So this comes from the change of base formula. You can check that out in the video that reviews properties of inverses. That is before this one. Now, if we know this conversion, this change of base going from the common log log to the natural log ln, if we know that this exists, then we can now take the derivative of a common log by taking the derivative of its conversion. And when we do that, I feel like this is spoilers. Let's actually just do that. When we do that, natural log of b, well, b is just some base number. So that's really just 1 over natural log of b is a scalar. We're going to multiply that by the derivative of natural log of x, which is 1 over x. So that's going to give us that if we have the derivative of a common log, oops, not equals, the derivative of a common log, that's going to be equal to 1 over natural log of b times 1 over x, or 1 over x times natural log of b. Now, let's pretend there's a function within that function. So instead of natural log of x, it's natural log of, let's say, u, where u is a function. That would just mean that we would have, so I'm going to write it like this, log base b of u, where u is a function of x. This is going to be u prime over u natural log of b. And that would just be if we have a chain rule situation happening within our natural log. So let's look at some examples where we have a common log. Whenever you see a common log, first convert it to natural log and then take the derivative. And still keep in mind these different properties of expanding and condensing, mostly just expanding in calculus, that are going to help us simplify what we're doing. All right, find the derivative of each function or equation. So the very first thing that I want you to remember is that you need to convert common log to natural log. While you're doing this, it also may help to expand anything that can expand. So instead of y equals log base 3 of this, I'm going to convert this to 1 over natural log of 3 times natural log of x times the square root of x plus 1 over 2. And then now I'm actually going to expand that common log portion. So expand the natural log portion. 1 over natural log of 3 times natural log of x plus 1/2. I'm turning that square root to a rational exponent. Natural log of x plus 1 minus natural log of 2. So I have not taken any derivatives yet. I'm going to do that now. 1 over natural log of 3 is just a scalar. The derivative of natural log of x is 1 over x. The derivative of 1/2 natural log of x plus 1 is 1/2 times 1 over x plus 1. And the derivative of natural log of 2 is 0. So let's just clean this up slightly. Y prime is going to be 1 over natural log of 3 times 1 over x plus 1 over 2 times x plus 1. Now, unless this is a multiple choice question and the answers have a common denominator and things are simplified, you don't need to worry about doing that basic algebra simplification. Okay, I'm going to do number 6 where there is some more space. So I'm going to just do this and we'll just bring number 6 down here. So first thing I'm going to do is rewrite it using natural log. So there's no base written, which means this is log base 10. So 1 over natural log of 10 times natural log of x squared plus 3x minus 5. So I have not taken the derivative. I have simply rewritten it using natural log. Now I will go ahead and take the derivative. I'm going to leave my scalar in front, 1 over natural log of 10. And I'm going to multiply that by 1 over x squared plus 3x minus 5 times the derivative of that denominator, or the derivative of the inside function, which is going to be 2x plus 3. And I'm going to clean this up a little bit. So 2x plus 3 over natural log of 10 times x squared plus 3x minus 5. So this is going to be my derivative here. All right, I encourage you to pause the video and try and work through number 7 on your own. Convert first, expand as needed, or use properties of logs as needed, and then unpause the video and see how you did. So here we go, first conversion, and then I dropped the exponent in front on this step. So now if I apply the derivative here, or if I take the derivative of both sides, I'm going to get 1 over natural log of 14 times negative 14 over x, which I guess I could just rewrite that as one fraction. Negative 14 over x natural log of 14 is my final answer there. So make sure you understand how to convert first from common log to natural log, how to expand, or the different properties of logs that we can use, so that we can then take the derivative of natural log problems. All right, the very last thing we're going to talk about is logarithmic differentiation. All right, so we have talked about the power rule and how if I have something like x to the power of 3 and I take the derivative of that, I drop the exponent down and I decrease it by 1. And in this case, when we have applied the power rule, we have been looking at a polynomial, or we have been looking at something where the base is the variable and the exponent is a number. But we haven't yet talked about what happens if the base is a variable and there's a variable component in the exponent. That same rule isn't going to hold. In fact, if you tried to do the power rule, you're going to go in this big circle and it's just not going to work. And it's not going to work because 3 in the exponent is not the same as having x in the exponent. And this whole premise of dropping the 3 down comes from the limit definition of derivative. That's what happens when we expand using the limit definition of derivative. So let's see if we can't figure out, knowing what we already know about logs, knowing what we already know about differentiation, if we can find a way to find the derivative of something like this. So if you think back to pre-calculus, anytime we had a variable in the exponent, what we were allowed to do to get that variable out of the exponent was we were allowed to take the natural log of both sides. So I'm actually still going to keep I'm not taking the derivative just yet. I'm going to take the natural log of both sides, and that allows me to move this exponent to the front. So still not taking the derivative quite yet. Natural log of y, and this is going to be x natural log of x. And now I'm going to take the derivative of both sides with respect to x. So on the left-hand side, the derivative of natural log of y is 1 over y, and we're going to multiply that by dy dx because of the chain rule, because we took the derivative of y with respect to x. And then this is the product rule, and we have done this. We did this problem already. We did it in number 3. So I'm going to save us a little time and just rewrite that we know that x ln x, if you use the product rule, is going to get you to natural log of x plus 1. Now, if I want to isolate dy dx, I'm going to multiply both sides by y. So that's going to be y times natural log of x plus 1. But we know what y is. Y is equal to x to the power of x. So we can rewrite this as dy dx equals x to the power of x times natural log of x plus 1. So this process where you first take the natural log of both sides to move that exponent in front, that's called logarithmic differentiation. And you can start to identify patterns and use shortcuts, but for right now, I really just want you to focus on this process. So anytime you see a variable in the exponent, know to get that variable down, the very first thing you're going to do is you're just going to take the natural log of both sides. There's no calculus there. That's going to move your exponent to the front. Once you have done that, you can then use implicit differentiation to take the derivative of both sides with respect to x. So that's going to give you 1 over y times dy dx. Over here on the right-hand side, I'm going to get natural log of x minus 2 when I use the product rule, plus x over x minus 2 when I take the derivative of natural log of x minus 2. Now I'm going to multiply both sides by y. So y times natural log of x minus 2 plus x over x minus 2. And I can substitute in what I know y is going to be. And you're going to do that every time you use logarithmic differentiation. So you can sort of skip this third step and jump immediately to this fourth one once you start feeling confident, or once you do it 3 or 4 times, you're going to just be used to it. So this is going to give me my final derivative. So the key thing here is that we're seeing a variable in the exponent. I want to get the variable out, so I take the natural log of both sides. Then I'm going to take the derivative implicitly, and then I'm going to solve for dy dx and make sure my final answer is solely in terms of x. I encourage you to pause the video and work through number 9 on your own, then unpause the video and see how you did. So natural log both sides, that's going to give you natural log of y equals cosine x ln x. Take the derivative of both sides. Make sure you're using the product rule on the left-hand side and implicit differentiation. That's why we have a dy dx tacked on. And then multiply both sides by y, and you can already see I skipped that step and just substituted back in what I know y is, which is x to the power of cosine of x. All right, now that we've gone through really what we need to cover in this first lesson of this section, I'm going to actually put up 2 more problems and have you kind of tie some things from previous sections together and see how you do. All right, as usual, I'm going to encourage you to pause the video and try and work through these 2 problems on your own first, and then unpause the video and see how you do. All right, hopefully you have given yourself some time to work through this. On number 10, we're looking for the equation of the tangent line. So we're first going to take the derivative because that is the slope of the tangent line. I need to find the slope at the point 0, 1. So first thing I'm going to do, x squared is going to become 2x minus 1 over x plus 1. That's going to equal 2y times dy dx, or y prime, minus 0. And then I'm going to solve for dy dx. You actually don't have to isolate it here. If you just want to plug in 0, 1, then you can solve it that way, whatever is easier for you. But I'm going to just say this is 1 over 2y times 2x minus 1 over x plus 1. And then we care about evaluating this at the point 0, 1. So that's going to give me 1/2 times 0 minus 1. So that's going to give me that the slope of my tangent line at the point 0, 1 is negative 1/2. Well, we have a slope and we have a point, so we can write the equation of the line. Y minus 1 equals negative 1/2 x, or you could rewrite that in slope-intercept form if you really want to. And then hopefully on number 11, you saw the very first thing I need to do before I can take the derivative is I need to take the natural log of both sides. Make sure I have parentheses here. Then I can take the derivative of both sides. So this is going to give me 1 over y times times dy dx. This is going to equal, something I want you to notice, natural log of 5 is not something that's a function of x. It's some number that's being multiplied by 3x squared minus 1. So in terms of derivative work, I don't have a product rule situation here. I need to take the derivative of 3x squared minus 1, which is 6x, and I need to multiply that by the scalar that's in front, or I guess that's behind, which is natural log of 5. This one looks actually much more complicated than it is. And then if I plug back in what I know y is, 5 to the 3x squared minus 1, that's going to get multiplied by 6x and natural log of 5. So key ideas in this video. We reviewed taking derivatives of natural log, and we analyzed some more complicated ones with chain rules and product rules. We used the change of base formula that we learned in Algebra 2 and pre-calculus to derive the derivative for the common log. How do we find the derivative of a common log problem? And then we practiced that. And then lastly, we talked about logarithmic differentiation, how we can pull variables out of exponents using that wonderful tool of logs, or taking the natural log of both sides, and how we can use that property. In the next video, we're going to build on something else that we learned using the limit definition. We're going to start talking about taking the derivative of exponential functions. So we'll review a little bit on the derivative of exponentials that involve e, but we'll build on that and talk about how do we find the derivative of something that looks like that but's maybe slightly different. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.